Hey guys, in this video we're going to discuss the codeforces round 875 that was rated for Dev 2. So we are going to discuss the first three problems, that is string permutations, array merging, and Copil, Copac, cross trees. I don't know why they give such complicated names, but anywho, let's get started. So the very first problem states that we are given with a permutation a of length n. Now the important observation over here is definitely that it's a permutation and it's not just a random sequence of numbers, but rather a permutation, right? We have to find a permutation b of length n such that a1 plus b1 is less than equal to a2 plus b2 is less than equal to a3 plus b3, so on and so forth, right? Now how would we do it? There would be multiple ways of doing it, but one of the easiest way would be not to make them less than, but rather to make them equal to. Let me prove that to you, that how that is always doable. So let's say we have some sequence, maybe like 5 4 1 3 2, correct? Now this is a permutation that would basically mean all the elements from 1 to 5 are present in it, right? Because this is a permutation of length 5. Now what I can do is I can say that I can make another permutation b, right? And when I'll sum individual elements from a and b, they would always sum up to n plus 1. Can I always do it? Let's check that. So over here I'm going to place a 1, right? That is 5 plus 1 is 6. 4 plus 2 is a 6, 1 plus 5 is a 6, 3 plus 3 is a 6, 2 plus 4 is a 6. So this also is a permutation, this also is a permutation, right? So the simple fact is that the greatest number in a permutation, in the first permutation I'm going to take that. To that I'm going to add the least number, right? Then I'm going to take the second largest number, I'm going to add the second smallest number to that, so on and so forth. So the number formed would always be n plus 1, or the summation formed would always be n plus 1, and this logic is always valid. So let's just also have a look at the code. The code is small actually. Initially I didn't actually read that it's a permutation, and I actually messed it up a bit. But yeah, this is the code. So you just have to print n minus I plus 1, where I was the element initially, that element from the array A that is initially given to you. Let's move to the next problem now. The next problem is array merging. So they say that we have two arrays A and B. Now we have to merge these arrays, and obviously we'll get another array of length 2n, right? Now what we have to do is that, okay, so there are some specific rules that you need to follow in order to construct this array C out of those arrays A and B. So you have to pick the first element of an array, right? So let's say I want to pick the first element of the array A. I can put that to the array C, right? Now the first element of the array A would have been popped out. Now I can select the first element of array B, or I can select the second element of array A, because the first element has already been popped out, right? So following that, I have to construct an array C. But now what we want to maximize is that the length of the subarray consisting equal values in C needs to be maximized. For example, over here, let's take this example, maybe this one, right? So if I say that, okay, firstly I'll pick this one, then I'll pick this 2, right? Then I'll pick this 2, right? So what would happen is that the final array would actually become 1 2 2 1. So in this final array, 2 is appearing 2 times, right? So the answer would be 2 for this. Now over here, I can I might want that I need to maximize the number of 2s in the final array, right? So what I can do is I can say that, okay, I'm going to start with this, then maybe I can use this. So the array I've already constructed, or the array C, is 1 2. Then I can pull up all of these 2s. So 1 2 3 4, right? So 4 2s and a 1 2 makes 5 2s, right? So we have 5 consecutive elements that are same. So 5 is the answer for this. Now what is the best way of doing it? I don't know what's the best way, but I know one of the optimal ways that definitely fits in the time constraints. So over here, it can be proven that it cannot be done in time complexity less than order of n, obviously. So we'll be able to do it in order of n time complexity. But what I'm rather doing is I'm using the concept of pockets. Now how do we use the concept of pockets is that okay, so let's say you have some element like 1 2, maybe 2 again, then 3, then 4, then 5, then maybe like 3 times you are having 5. Okay, let's segregate that. Yep. And then you are having a 7 and maybe a 7 again, right? So when I'm saying pockets, I know that there's a 1 appearing over here, then there are 2 2s, right? Then there's a 3, then there's a 4, then there are 3 5s, then there are 2 7s, right? So this is what I know. I can extend this thing further. How can I do that? Now that's where it's not tricky, but implementation actually matters over here a bit. So let's say this was my array A, right? I'll do the same procedure for array B as well, right? So for array B also, I'll get this particular pockets, right? And one thing I'll do smartly over here is that I don't care about, so let's say a particular element, maybe like 3, had multiple pockets. So in order to just draw that, what I can say is that, let's say, okay, let me make a array bigger. Yep. So maybe like 3 was appearing over here, then there was from 1 to 7, and then 3 was appearing over here as well, right? Maybe like four times now, and then there was 8, let's say, right? So the pocket over here, this particular pocket or this particular set actually contains 3 threes, right? And this contains this contains 4 threes, right? Now I just need to check for the maximum value available. I'm not even concerned about the lower value available. So in a array, so this, if there's an array A, in the array A, I just need to know how many maximum number of occurrences occur in a pocket for a certain element, right? So appropriately, I'll be updating this particular array, or this is not an array in my implementation. This actually becomes a hash map. Multiple things could have been used for it, but hash map like seemed to be the right choice for it. Hence I used that. Now for B also, I'll be doing the same process. So after that, I'll be having 2 hash maps. Let's call them hash map A and hash map B. So hash map A would be having the value, and corresponding to that, it would say that how many maximum number of times does this particular element having the value val occurs, right? So it'll say that, okay, 3 was occurring 4 times. So that's what it'll contain, right? B would also contain some similar value for the array B. And now what I can do is I can say that, okay, this particular element 3 is occurring 4 times over here, right? Now I also want to check how many number of times does it appear in the array B. Now maybe in the array B, 3 appears at max X times in consecutively. So I can add these 2 values, X from here and a 4 from here. I can add them up and I can make them X plus 4, right? So similarly, I'll be doing for all the values. So there could be like n values, right? For all the values, I'll be doing this. So time complexity would be order of n, right? And finally, I'll be having my answer. That would actually work. Cool. Let's go through the implementation. Yep. So I'm having 2 maps, F1 and F2, right? And this is one way of checking the pockets. You could have utilized other ways. So I'm actually going up till n, right? Up till n. So what I'm doing is, if I is equal to n, the problem actually becomes that if I try to access the element at the index I, that would be a wrong, illegal reference maybe. So I don't want to do that. So if I is equal to n, I know I have reached the end, right? I just need to update the variables. So I'll be doing that. So I'll say that, okay, whatever value was there in the previous element. So if you are already at I, right? So the I, okay, your I is equal to n, right? So I minus 1 values would your I minus 1 would be having some value, and it's possible that it was being repeated multiple number of times, right? So you'll say that whatever value it had. So this is the value A of I minus 1. You need to put the maximum value into that. So it could be possible that it appeared multiple number of times in the previously also, right? And it's possible that now also it appeared some C1 number of times. So whatever bigger value would be, that should be available in F1, right? And similarly, you'll be doing for the array B, that would contain the values in the hash map F2, right? And then you'll break it. So breaking over here is actually important, else you might get into a scenario where you or you would get into a scenario where you'll be trying to access the index I, and that would be wrong, right? So you'll be doing that. After that, you'll say that if your current element is not equal to the previous element, that means the previous element definitely has some occurrences, and now you need to store them because you cannot go further with them, right? So you'll say that, okay, you'll update the values similar to this, right? And then you'll set the current occurrences. So the current occurrences actually would mean the number of occurrences of the value A of I. So you'll set them to 1. If that's not the case, then definitely the element at the position I and the position I minus 1 are similar. So you'll update that. You'll increment your pointer C1. So, or the integer C1. C1 basically means how many number of consecutive elements are there in the array A. Now the exact same procedure needs to be followed for the array B as well. So you'll be doing that. After that, what you'll say is that your result is equal to 0. So initially we are saying it's 0, right? Although you could have actually set it to be 1 and things wouldn't have changed, because minimum answer would always be 0 in case you have a non-empty array, right? And then you're gonna go through all the values in the array f1. You're gonna set the result to max of whatever value result has, or x plus x is the number of occurrences or consecutive occurrences of the element n in the array A, right? So x plus the number of occurrences of the element n in the array B, right? So you'll do this, and then you'll do a similar procedure for the array B as well, or the hash map for the array B as well, and at the end you'll be having the valid answer. So yeah, this works. This I've already submitted and it's fine. Next, let's move to the last problem. Last problem is a bit interesting. So the problem states that Copil Copac is given a list of n-1 edges describing a tree of n vertices. He decides to draw it using the following algorithm. So in step 0, he would draw the first vertex, that is the vertex 1, and go to the step 1. So just take care of the steps over here. So step 0 is drawing the vertex 1, and nothing else needs to be done as of now. In step 1, for every edge in the input, in order. So this is the important thing. If you miss this out, your answer is going to be wrong. In order basically means that you are given all of these edges, right? So you have to make sure that 4, 5 is coming before 1, 3, it's coming before 1, 2, it's coming before 3, 4, and it's coming before 1, 6, right? So the order actually matters over here. So for every edge in the input in order, if the edge connects an already known vertex u to a undrawn vertex v, right? He will draw the undrawn vertex v and the edge. After checking every edge, go to step 2. I hope this makes sense, right? So firstly you'll be checking that if there's a edge u that is available in your array, or is already drawn by you. So at the very first step, or the step 0, you would have only drawn the vertex 1, right? Now you'll basically check that, okay, is there any vertex with the value which can go from 1 to some other vertex? If there's so, then you'll draw that. Let me just give you example. In step 0, let's say you draw vertex 1, right? You'll come to step 1 then, and then you'll start going through this edges, right? So you'll say, okay, 1, 3 is available, so you'll draw 1, 3, right? This is 1, 3. Then you'll say 1, 2 is available, you'll draw 1, 2. Then you'll say 3, 4 is available, right? Okay, 3 is already over here, so let's draw 3, 4. Then he'll say 1, 6 is available, then he'll draw 1, 6. But wait a second, 4, 5 is something we didn't draw, right? So why didn't we draw 4, 5? If you look at it, right? So 4, 5 actually came at the first. At the time we checked for 4, 5, there was no edge 4 in this array, right? Because initially the entire tree we were having had a single node that was vertex 1, right? So we went with that, and we started constructing a graph. Now what would happen is step 1 actually concludes over here. We go to step 2 and we check if all the vertices have been drawn, then we terminate, else we go back to the step 1. And now with this particular graph, we'll be going back to the step 1, that is going through all of the edges available. So now we'll be able to see that, okay, yeah, there's the edge 4, 5. Do we have 4 in the array? Yes, we have a 4 in the array, so we'll draw the edge 4, 5 as well. So yeah, that's it. That's it for the problem. I hope I was able to at least explain you the problem. Now let's go for the solution. So solution, naively, it's a very easy problem. So you can say that, okay, I'm gonna draw the tree. So you'll start drawing the tree, and at every whenever you complete with the step 1, so on completion of step 1, right, you'll check the entire edge list in order, and then you can proceed further, right? The only problem over here is it's an order of n square solution. Now one might argue that how is that? So the simple reason is that, let's say you had n-1 pairs, you obviously would be having n-1 pairs or n-1 edges, because it's a tree, right? So let's say this was some x to y, this was some y to z, so on and so forth. There were so many edges, and this is the step 1, let's say, right? And let's say this last one is a to b, right? Second last one is a to b, and the last one is maybe like 1 to a. Now in step 0 you drew a 1, and when you'll come to step 1 you'll say that okay, you traverse through everything, and then you find out that okay, there's one edge at the end, so you'll draw 1 to A, right? You'll go to step 2, and now again from step 2 you'll come back to step 1, you'll start proceeding again, and at the very last you'll find a to B, right? So you'll draw A to B. Now maybe there's a edge B to C, like over here, right? So in the next iteration you'll find B to C, and so on and so forth, right? So basically you'll need n iterations, and in each of the iterations you were checking the entire edge list, right? So it actually becomes an n-square algorithm. Now how can we reduce this? So we can use a basic data structure that is similar to the adjacency list, just a bit of variation over here. So what we can do is that whenever we are making an adjacency list, right? So we generally say that okay, for edge goes from U to V, so we write that as in the adjacency list of U we put a vertex V, right? But over here what I can say is in the adjacency list of U, let me put V comma the index. Now what's the index over here? Index basically means that what index this was happening. So this is index 0, this is index 1, this is 2, so on. This was n-1, this was n-2, this was n-3, right? So at what index this is happening, that is something I'll write down. I will come back to the point that why are we doing so, but for now let's just remember that we are going to proceed in this particular fashion. Now what I can say is that initially I'm going to start at 1. That's something I know, right? So let me start at 1, and then I'll say for all the vertices that are connected to 1, right? So that would be stored in this particular adjacency list, or that would be stored in an adjacency of 1, right? I'll say add it, right? So it will start adding it, X, Y, Z, and let's say this is a DFS call, right? I hope if you're doing the problem C, you at least have an idea about the DFS problems, or you have an idea how DFS works or how recursion works, right? So some nodes would be connected to this, and initially since it was 1, I could have given it a dummy index, because 1 actually automatically comes in the step 0, so I could have given it a dummy index of -1 maybe, right? So with -1 it starts. Now let's say over here it says that okay, the index of the edge 1 to X was 2, right? So the index or the place at which this edge was added, right, that was second index. So in the DFS call itself there would be a value that would state the index, right? So it will know that okay, I'm already at the second index. Now this tree would keep on growing, right? So this tree would grow. Now X would say that okay, I have maybe like 4 more vertices. Let's call them A, B, C, D. B is already over here. Let's cut that. Okay, A, B, C, D. Now the beauty is that over here we said that this is the second vertex, right? Or this was the second edge. So 1 to X was the second edge. Now because 1 to X was the second edge, we would have X once we had traveled through the first and the second edges. So for all the edges that are after second, we would already be having X as one of the components, right? But in case of the first edge, now let's say first was the edge maybe like X to let's just say theta, right? Let's say it was X to theta, but when we'll push X, right? So we are pushing X at the second index, and X to theta is an edge that was present at the first index. So this won't make any sense because at this time we won't be having it, right? So that's why it matters. Now, because as you'll go from X to theta, right? So let's say X to A was the third edge, X to B was the fourth edge, X to C was the fifth edge. That's all fine because you already have X by that time. But as soon as theta happens, so theta is, let's say, the first edge itself in the entire graph, right? Or in the entire ordering that's given to us. So he'll say that, okay, since you are coming before it, in the same iteration, I cannot process you, right? Because by the time I would have come to you, so when I would have come to you for the first edge, X wouldn't itself be in the graph, right? So it'll say that, okay, I'm going to process you, but you're going to come at the next iteration, right? So it'll say that, okay, iteration is going to increase. So the DFS call would actually maintain the iterations as well, and it's gonna say that iterations are gonna increase for you because your edge is present at a location that is before the time this particular edge was connected, right? And that's how we're gonna do it. Now I hope that the logic is clear. If it isn't, I'll really suggest you to rewind the video back a bit, because I feel this is a bit tricky, but I think I was able to explain it well. But it's still, if you still have doubts, then definitely let me know. But I'll really recommend you to go back a bit and try to rewind it. Let me show you the implementation. This implementation is fairly simple. So I'm just taking all the edges. I'm constructing the adjacency list. But over here, the only thing is that in the adjacency list, along with the pairs u and v, I'm also having the index at which this node is being added, right? Or this edge is being added. Then I'm going for a DFS call. So I'm saying do a DFS call for the vertex 1, y1 over here, because I've already subtracted 1 because they were giving the array in 1 base indexing. I wanted it in 0 base. So I just subtracted 1 over here itself, right? And after that, I make a DFS call. In that DFS call, I set my answer to the maximum of the current answer or the iterations, right? Why I'm doing this iterations over here? Because iteration variable right over here actually gives me that at in which iteration I am, right? So in the very beginning, we go from step 0, then we go to step 1, right? So the first time we go to step 1, it's the iteration 1, right? But when we'll be coming again and again, so we basically had to calculate the number of iterations required. So that's what this iteration suggests. Then we have a variable idx, right? So idx basically states that idx basically states that what is the index location of the parent when it was added, right? So initially we are saying we are going to go from the 0th index. We are going to pass the adjacency list. We are going to say that the parent is -1 because technically the 0th node doesn't have a parent. So let's just give it a dummy fake value. The iteration is the first because we already talked that it's the first iteration. Then we are going to give it an index, right? So what index should I give it? Because the node 1 is automatically added. So I just need to give it a fake index. That is actually minimum, right? So we can give it -1. After that, I'm going to say that answer is maximum of answer or iterations. Then for all the children it's having, I'm just going to check it shouldn't be the parent itself, right? Otherwise I'll get into a continuous loop. So if it's not so, then I'm going to make a DFS call for the neighbor or for the child, right? I'm going to pass the adjacency list. I'm going to pass the current node. And now the number of iteration might or might not increase depending on what the value is of the current ID and what was the value for my parent. Now this was the value for my parent. This is the current, right? So if current was happening before the parent, then in the same iteration, I cannot add it, right? So if that is happening, then a +1 would be added. And finally, I'm going to pass the ID. So yeah, that's the implementation. You can try it out for your own. I've already submitted it and it's giving the AC. Cool. I hope you understood the solution. If there are still any doubts, let me know in the comment section below. Cool guys. Thanks a lot for watching this video. Bye bye.